This video is going to be a solution to this problem that I posed where you have a disk that's rolling down an inclined plane and you want to find what the velocity of the disk is at the bottom. And what you saw in this problem was there's actually two ways to do this, and one is certainly quite a bit more algebraically intensive than the other. So we're going to go through both ways here. So in the statement of the problem, it tells you that you have this disk that's going to be rolling down this inclined plane. It starts from rest, and what we'd like to do is we'd like to determine what its velocity is at the bottom. So the first way that you can approach this is by using kinematics and Newton's laws. So approaching it like this, what we say is we first need to have some free body diagram. Okay, so here's our disk, and we know that gravity is acting at its center of mass, which is the center of the disk. Then we're going to have some force of friction. I'm just going to call for the time being lowercase f. That is going to be opposing the direction of motion, and ultimately this is what's causing it to roll. And there's going to be some normal force. So normal force, I'm going to just define like that. Okay. So then once we have our free body diagram, the next thing that we want to do is to draw some coordinate systems for this. And so the coordinate systems that I'm going to choose are first going to be in the direction of motion and perpendicular to the direction of motion. And I'm going to define a second coordinate system here that is going to be the direction that this is going to rotate. So when we're summing our torques, this is important because we have to say whether the torque is positive or negative relative to the coordinate system that we drew here. Okay. So once we have our coordinate systems, we're ready to start writing Newton's laws. So we have sum of the vector forces is equal to the mass times the vector acceleration, and the sum of the vector torques is going to be equal to the this is the moment of inertia, I, times the angular acceleration, alpha. So now what we want to do is we want to break this apart in x and y for our forces, so the sum of forces in the x direction. Here we just have some minus f, force of friction, and then some component of gravity here. And so because of the way I define this angle right here, this is going to be the angle here. So that's going to be theta. And so then we also have this plus mg cosine of theta. And then this is going to be equal to the mass times the acceleration in the x direction. I'm just going to call this a, because that's really the only linear acceleration we're going to have. Now what we can do is we can sum our forces in the y direction. So sum of forces in y is going to be equal to n, and then this is going to be minus capital mg sine of theta. And this one happens to be equal to 0 because it's not going to accelerate at all in y. So what this allows us to do is we can actually find what our normal force is right off the bat. So we have normal force is equal to mg sine of theta in this particular case. And I just realized that I call this angle phi here, so let's use phi instead of theta. So this is cosine of phi, sine of phi, sine of phi. Okay. So now this is kind of the interesting part, and the part that's new for this section. We need to sum our torques. And so we remember that torque, by definition, is going to be equal to R cross F, which is going to be equal to magnitude of R times magnitude of F times the sine of the angle in between R and F times n hat. Okay. Now we have to be kind of careful with this because we have the sine of some angle, but this is not the sine of the angle that we have here. Okay, where this angle is the angle phi. Okay, it's the sine of the angle in between. The sine of the angle in between R and the force that we're talking about when we're finding that torque. So when we're summing our torques here, there's actually only one force that causes torque about the center here, and that's going to be the force of friction. And so when we look at this, we have the torque is going to be equal to R, the distance from the point of rotation to where the force is acting, which is just the capital R. This is the radius of R. Okay, so here's our radius of R. I'm going to draw this in. Well, we'll leave it the way it is. So this is radius R times the force, which is going to be force of friction F, times the sine of the angle between them. Where here, this is actually going to be 90 degrees. And so because that's 90 degrees, this is going to be the sine of 90, which is going to be 1. So let's just get rid of these guys and then go back there. So our free body diagram only has forces on it. Okay, so we have R times F, and we can be really explicit. We're saying that this is plus because it's in the direction that we define to be positive for rotation. Okay, and this is going to be equal to I times alpha. Okay, so now we have our system of equations, and that was actually really C. So this is what I have here is B and C. But we're just going to kind of continue the problem without regard to exactly the way I defined it here. Okay, so now let's summarize the equations that we have. We have mg times cosine of phi minus f is going to be equal to capital MA, and then we have R times F is going to be equal to I alpha. And the equation for the normal force actually isn't important here. Okay, so 2 equations and 3 unknowns, because we don't know what F is, we don't know what A is, we don't know what alpha is. But there's some relationship between alpha and A. So we can say that alpha is going to be equal to A divided by R, or A is equal to R times alpha. And we also need the moment of inertia. Here we have the moment of inertia of a solid disk, which is going to be 1/2 capital M R squared, I believe. Okay, let me just check that I put that in the statement of the problem. I tend not to remember these. Okay, yeah, 1/2 M R squared. Okay, good. So now what we want to do is we want to substitute this information in here. So when we do this, we say that this bottom equation is going to become R times F is going to be equal to 1/2 capital M R squared times alpha divided by R. And so we can see that one factor of R is going to cancel from this side, and then a second factor of R is going to cancel. So ultimately what we have is, for our 2 equations, we have mg cos phi minus F is going to be equal to capital MA, and then we have F is going to be equal to 1/2. This is not an alpha, this is an A. This is an A. So we have 1/2 A. So we have 1/2 capital M A. And then what we do is we just add these together. So we add these directly together. And the reason why we're doing that is because we see that we have a negative F here, and we have a positive F there. Those are going to cancel. And then we're left with mg cos phi is going to be equal to 3/2 M times A. And so A, the acceleration, which is ultimately what we're looking for, A is going to be equal to, our M's are going to cancel. We multiply both sides by 2/3. And this is going to be 2/3 G cosine of phi. So this is the acceleration of the disk down the plane. Okay, so then, hopefully I've not been frozen too long. Let me fix that very quickly. So we have the acceleration down the plane, and once we have the acceleration down the plane, then this happens to be constant acceleration. We can find the velocity as a function of time by saying that this is just going to be from our kinematic equations that either we remember or we know how to derive from. A is going to be equal to dv dt, and v is equal to dx dt. We have these 2 equations. X0 plus v0t plus 1/2 a times t squared. So we have these 2 equations where the initial velocity is 0, so we're starting from rest, and we can define our coordinate system here so that x is 0 as well. So we want to find how long it takes for this to, what the velocity is when it gets to the bottom. So in order to do that, we need to find out how long it takes to get to the bottom. And so here we have this distance of d, and so what we say is that x of t is equal to some special time. It's going to be equal to the distance d, which is going to be equal to 1/2 a t star squared, and then solve for t star, because that's the time that it takes to get to the bottom. So when we do that, we see that t star is going to be equal to 2d divided by a, 2d divided by a with a square root. Okay. So now that we have this, what we want to do is we want to take this and then evaluate the velocity at that time. So we say we want v of t is equal to t star, and this is going to be equal to a times t star, which we just found is the square root of 2d over a. So with our a's here, we really have a times a to the minus 1/2, and so this becomes a to the 1/2, so this is going to be the square root of 2dA, and then we can plug in our a into this, and so we see that v of t is equal to t star which we could write another way. We could say this is the velocity at the distance d. This is going to be equal to 2 times d times 2/3 g cosine of phi with a square root. And then the 2 can come on the outside. To simplify this the way that I had it there, what I did was I just multiplied this by root 3 over 3. Root 3 over 3. And so this says that VD is going to be equal to 2/3 times the square root of 3d times g times cosine of phi. Okay, so that's what our answer is going to be. And you see, I did end up kind of skipping around and doing some steps very quickly with the algebra. And you don't really need to worry as much about that. The most important thing is, can you set up these equations? Can you draw a free body diagram? Can you set up the equations from it? And then from there, it's algebra, and that's not really what we're testing is your algebra skills. We're testing your physics skills. Can you model this situation and set up the equations for it? Okay, but this is the answer that we end up having, and the takeaway from this is a very long process to do it like this. What's easier is doing this the second way. So if we look at part D, doing this via conservation of energy. Okay, so for part D, what I think I had you do is I had you draw energy bar charts. So you had your kinetic energy, but this is really broken into two pieces. There's the translational kinetic energy, the kinetic energy of something just going like this, and then there's the kinetic energy of something rotating. Okay, and so here we actually have both, right? So we have the kinetic energy of translation, kinetic energy of rotation, and we have gravitational potential energy. And then we're going to list these on the other side. U, G. Okay. So at the beginning, we have all gravitational potential energy. At the end, we have some combination of kinetic energy due to translation and kinetic energy due to rotation, and some amount that we don't know exactly what it is to represent on here, but we know we have some of both of those and no gravitational potential energy at the end. Okay. So what this says then is I remember that my gravitational potential energy is mgh, my rotational kinetic energy is going to be 1/2 I omega squared. My translational kinetic energy is 1/2 mv squared. And I can use the fact that omega is equal to v divided by r, and I is going to be equal to 1/2 m times, oops, that's a funky m there, m r squared. And I'll use this in a moment when I make the equation. So really what we're doing is we're saying that E1 is equal to E2, where this is going to be mgh. mgh is going to be equal to 1/2 I omega squared plus 1/2 times m, capital M, v squared. Okay. And so then we need to find what h is, because we're not told what h is, right? We're told what d is. That's not a big deal, because we just do a little bit of trigonometry here. We have d, which is the hypotenuse of the triangle, and phi, which is the angle between d and the vertical. And so what that tells us then is that the cosine of phi is going to be equal to, this is going to be equal to h divided by d, or h is going to be equal to d cosine of phi. And then let's start evaluating this. So we have capital M g times h, which is going to be d cosine of phi, is equal to 1/2 times I, which is going to be 1/2 capital M r squared, times omega squared, which is going to be v divided by r quantity squared, plus 1/2 capital M v squared. So the first thing that we can see here is we have an m that's common to all of the terms. We can cancel that. Let's get rid of our m. We also see that this r here is going to cancel this r. So let's cancel that. So let's write our next step now. So this is going to be g times d times cosine of phi is going to be equal to 1/2 times 1/2 is 1/4 times just v squared, and then plus 1/2 times v squared. 1/2 plus 1/4 is 3/4, so this is going to be 3/4 times v squared is going to be equal to g d cos phi, and we're almost there. We just need to multiply both sides by 4/3 and then take a square root. And so when we do that, we end up seeing that v is going to be equal to the square root of 4/3 g d cos phi. And then we can bring the 4 on the outside, multiply by √3 over √3. And so then we have 2/3 times the square root of 3 times g d cos phi. And in a much more expedient fashion, we ended up finding we have exactly the same answer for both of these. Okay. Now it might not. It does look like more here, but it is even more than what I wrote when you're doing this, because I went through the algebra very quickly. Whereas this one, there's really not so many more steps than what I wrote here anyway. Okay. So that's going to be it for this video. Okay. Take it easy, guys.